Good afternoon, students. Today, in this video, we are going to discuss about Unijunction Transistor sweep circuit. So, before proceeding for that, let's try to understand what is a Unijunction Transistor, how it actually works, and how it actually gets constructed, and its characteristics. So, this is how the construction of a UJT is shown here. So it compared to BJT, which is having two PN junctions in it, this UJT is having a single PN junction. This is made up of a P-type material alloyed with a N-type slab, and it is having two bases, base 1 and base 2. These two bases are actually ohmic contacts. The PN junction is formed between P-type emitter and N-type silicon slab. Since it is having actually two bases, it is originally it was named as double based diode, but now it is getting called as a UJT. The equivalent circuit representing the diode action and its ohmic contacts of base 1 and base 2 is shown in figure B. The PN emitter and base junction is represented in terms of diode, and these base 1 and base 2 ohmic contacts are represented with the help of resistances RB2 and RB1, where RB2 is the resistance between base 2 and emitter, and RB1 is the resistance between base 1 and emitter. One thing to be remembered here is the resistance RB1 is actually variable and RB2 value is fixed. How this RB1 resistance gets variable will be discussed in the coming concept. Now coming to the operations of this device. So let us say this junction diode, PN junction diode, conducts only when it gets a sufficient positive voltage, which is emitter voltage here. For example, so when IE is 0, when the emitter current flowing through this diode is 0, then the circuit is simplified as shown in figure C. Since this IE is 0, this becomes open circuit and we won't get any current flow through diode. Diode will be purely reverse biased right now. And in this circuit, if IE is 0, there exists a current I through RB2 and RB1, and the voltage across RB1 is termed as V1. Here V1 equals to can be noted with the help of a voltage divider formula. So V1 equals to VBB into opposite resistance by total resistance, which is, if IE is 0 due to the applied voltage VBB, so I equals to VBB by RB1 plus RB2. The voltage across this RB1 V1 equals to I, the current flowing through the resistor RB1 and into RB1, which is VBB by RB1 plus RB2 into RB1. Now here comes a important term called intrinsic standoff ratio. The ratio of RB1 divided by RB1 plus RB2 is termed as intrinsic standoff ratio, which is denoted by eta. Therefore, if we substitute eta in place of this, then the voltage across this resistance RB1 is V1 equals to eta into VBB when the emitter current is 0. Coming to the characteristics of UJT, let us consider the same figure, equivalent circuit of UJT as shown in figure B, and UJT is represented in terms of symbol as shown in figure A here, with base 1 and base 2 and emitter. Now this emitter junction diode, which is this diode in between emitter and base 1, so unless this diode is turned on, means from the circuit the diode cannot conduct unless the emitter voltage VE exceeds the threshold voltage and the voltage V1, means the summation of V gamma plus V1, and until unless the emitter voltage exceeds V gamma plus V1, this diode does not conduct. And if you observe these characteristics here, right, so when it is not conducting, means when the diode is not conducting, the UJT is completely off, so that is called a cutoff region. See, in these characteristics, the diode will conduct only when it reaches the value of VE is greater than V gamma plus V1. That point where the diode actually starts conducting is called as peak point or peak voltage, denoted by VP in this figure. This is the maximum voltage or the minimum voltage required to make this UJT to turn on. This peak voltage, once the diode is turned on, it enters into a on state, and as the voltage goes on increasing, the emitter current which is flowing through this diode also increases. As more current is flowing through this resistance, like IB2 as well as IE, so the resistance value of this RB1 tends to fall down. So as the current increases in this VI characteristics, x-axis takes current and y-axis is emitter voltage. As the current goes on increasing, this resistance from this peak point, it goes in a negative direction, means the fall of resistance happens in this region. That's why it is particularly named as a negative resistance device, and the region in which the resistance RB1 falls down is called as negative resistance region, and it falls down to a least value called V valley point VP. And after that point, means after that point is crossed, then the transistor, the unijunction transistor, enters into a saturation region. As you see, the graph is divided into three parts. The point before which the diode does not conduct, means when VE emitter voltage is less than V gamma plus V1, it is in cutoff region. The current what it is flowing here represented as a leakage current, which is a reverse saturation current. And after the diode voltage, which is VE, has crossed V gamma plus V1, so it enters into on state. So when the current goes on increasing, so here the resistance gets reduced and the voltage also gets reduced. After this P valley point VP, then still the current goes on increasing, then the transistor, the diode will heavily conduct and the transistor enters into a saturation region. See, the value of the diode which makes this diode conduct is termed as peak voltage, denoted by VP. VP is equals to V gamma plus V1, and since V1 equals to eta VBB, which is derived in the previous slide, so substituting that we get VP equals to V gamma into plus eta VBB. So as we see, it is the explanation of this graph. When VE is less than this peak voltage, the UJT is completely off, means it will be in cutoff region. And when emitter voltage crosses VP, crosses the VP peak voltage, then UJT is on. This is what the explanation of UJT and its characteristics. Let us move on how this unijunction transistor is used to design a sweep circuit. In the previous exponential sweep circuit, we saw that we have taken a switch across a capacitor which is connected to a resistor and to a supply voltage. So this UJT transistor is now getting used as a switch in terms of in place of S in exponential sweep circuit. Like this, The figure shows an exponential sweep circuit in which UJT serves as a switch. Previous case we used to have in exponential sweep circuit, we had a switch across this capacitor. Now we are taking this UJT as itself as a switch here. The supply voltage VYY and the charging resistor R must be selected such that the load line intersects the input characteristics in a negative resistance region, means in active region. Assume that UJT is off initially. The capacitor, when this is off, this capacitor will have a direct connection to VYY through R. The capacitor starts charging through resistor R in an exponential way. The capacitor charges from VYY through R. When it is charged to a sufficient voltage called peak voltage VP, immediately the UJT turns on and now the capacitor discharges through the UJT. When the capacitor discharges through the UJT to a value called valley voltage VV, then UJT again turns off. When UJT is turned off, then again this capacitor gets charged from VYY through R again in exponential way. This cycle repeats continuously. So here this UJT is actually serving a purpose of switch. Now see, the capacitor voltage as shown in figure D and the expression for sweep time Ts can be obtained as follows. As we said that the capacitor gets charged from VYY in an exponential way. When it reaches to a value called Vp peak value, immediately the UJT turns on, then the capacitor starts discharging in exponential manner. And when it reaches to a value called valley voltage Vv, then again the UJT gets turns off and the capacitor starts charging again from VYY through resistor R. So this cycle continues and it generates a exponential signal like this. So considering from 0 less than t less than ts, means during this duration it is exponentially increasing waveform. As we see, what is the final value up to which the capacitor can charge is actually VYY from the circuit. So the final value is VYY and the initial value is VV here. Substituting that in an exponential generalized equation, then the sweep voltage Vs equals to VYY minus of VYY minus VV into e power minus t by RC, where VYY is the final value and VV is the initial value representing the exponential form of equation. Now at t equal to ts, means at the end of this sweep time, what happens at t equal to ts, this Vs sweep voltage becomes a Vp. So substituting that Vp and t equal to ts in this equation, it becomes Vp equals to VYY minus of VYY minus VV into e power minus ts by RC. Why ts? We are considering at that instant t equal to ts. At this instant the value of V0 or Vs is Vp and t equals to ts. Substituting this, we get this equation. From this, simplifying this, taking VYY to the left hand side, it becomes, and simplifying this equation, and we can derive ts equals to RC natural log of VYY minus VV by VYY minus VP. And to derive the frequency of oscillation f equals to 1 by t. Here the total time period t is the sum of the sweep time as well as the restoration time or flyback time tr. So f equals to 1 by t, where capital T equal to ts plus tr. Substituting this, f equals to 1 by ts plus tr. Neglecting tr, since tr the restoration time is comparatively small when it is compared to capital Ts, so ignoring that, f equals to 1 by ts. So substituting this entire ts value, which is RC ln of VYY minus VV by VYY minus VP, so in this equation it becomes 1 by RC natural log of VYY minus VV by VYY minus VP. So now considering this value voltage, which is VV, is very small when it is compared to the maximum value, which is VYY. So since VV is very less than VYY, ignoring that in the numerator term, it becomes 1 by RC ln of VYY divided by VYY minus VP. So F equals to, taking this into the denominator here, F equals to 1 by RC ln of 1 by 1 minus Vp by Vyy. Now the peak voltage Vp, what we have derived in the previous slide, it is a V gamma plus eta VBB. Now considering this VBB is approximately equals to Vy, the maximum value Vyy, then this can be written like this: V gamma plus eta Vyy. Now Vp equals to eta into Vyy. Again, by neglecting this diode voltage V gamma, which is very comparatively very less than Vyy, so this can be written in terms of Vp equals to eta Vyy. So from this, eta equals to Vp by Vyy, which is intrinsic standoff ratio eta. Now substituting eta in place of Vp by Vyy in the frequency equation, we will get F equals to 1 by RC natural log of 1 by 1 minus eta. This is frequency of oscillations of this UJT circuit. So for producing a good linearity, the sweep voltage should be Vp minus Vv. We should be much smaller than V equals to Vyy minus Vv. Usually the peak voltage will be very much greater than the value voltage, and similarly the Vyy voltage, supply voltage, will also be very much greater than Vv. So we require Vp less than Vyy and V greater than Vbb to produce a much linear signal. So when this Vv is very small, then we can justify the relation between ES, ET and ED in terms like this: ES equals to TS by RC, ET equals to TS by 2 RC, ED equal to TS by 8 RC. So this is how we derive frequency of oscillation, and we understand the working of UJT sweep circuit, in which UJT transistor is actually used as a switch in generating a sweep signal like this.